Welcome viewers to the first lecture for the online series of lectures for the course of Algebraic Topology 2. In the last two lectures for the course of Algebraic Topology 1 offered in summer 2021 in BRAC University, we discussed basics of simplicial homology groups. There we computed simplicial homology groups of certain simplicial complexes, for example. In this lecture, for the course of Algebraic Topology 2, we will start with the computation of simplicial homology groups of certain compact surfaces. For example, we will compute the homology groups of two torus, Klein bottle, and real projective plane. Before we do that, let me recap a few notions from the course of Algebraic Topology 1. We denote by K a finite simplicial complex. By Cp of K, we mean the group of P chains on the complex K. Okay, Cp of K, we have seen it in Algebraic Topology 1 that this is a free abelian group. And since it's a free abelian group, it has a basis. It's a free abelian group with the elementary P chains corresponding to the oriented P simplices of K as its basis. Okay. Since there are finitely many such elementary P chains, it is of finite rank, and hence it is of finite rank. Okay. Now, by Zp of K, we denote the group of P cycles and this group of P cycles is a subgroup of the group of P chains. Okay. Recall from the course of AT1, Algebraic Topology 1, that Zp of K is the kernel of the following map, is the kernel of the following map, which we call the boundary operator, right? Del P from Cp of K to Cp minus 1 of K. Right? Since Cp of K is free abelian, okay, of finite rank, in other words, it's finitely generated free abelian group. Hence, since this is the case, Zp of K, which is a subgroup of Cp of K, has to be a free abelian group as well of finite rank, according to one of the results from from the theory of free abelian groups, right? ZPK being a subgroup of CPK, subgroup of CP of K is free abelian of finite rank. Good. Therefore, we conclude that the pth homology group HP of K, which is defined as the quotient group of ZP of K modded out by the P boundaries on the complex K, is this guy is finitely generated. Okay. So it's a finitely generated group, and from the fundamental theorem of of finitely generated abelian group, it has a free part, and a torsion part, right? So HP of K is a finitely generated group, and by the use of the fundamental theorem of finitely generated abelian group, we know that it has a free part and a torsion part. Okay. The Betti number and torsion coefficients corresponding to the free part and the torsion part respectively of HP of K, which is a finitely generated abelian group, are called classically the Betti number and torsion coefficients of K in dimension P. Okay. Good. So in the present lecture, we'll compute the Betti numbers and torsion coefficients of compact surfaces. So present lecture is dedicated to the computations of Betti numbers and torsion coefficients of compact surfaces. Okay. All right. So this was a brief review of what we did in Algebraic Topology 1. So we begin our first lecture with Lemma 1, with the lemma, which will turn very useful in computation of homology groups of the underlying compact surfaces. Okay. Let L be the complex shown in the figure below. It refers to the following figure on the left. There will be two figures drawn. So let me draw these two figures. There is a complex here. Whose underlying space is a rectangle. Okay. Whose underlying space is a rectangle. By rectangle we mean this region, this entire region bounded by this this shape, this one-dimensional shape. Okay, so this is what we mean by a rectangle. Let BDL denote the complex whose underlying space is the boundary of the rectangle. So now we orient each of the two simplices counterclockwise direction, in the counterclockwise direction, like this. Each of these two simplices sigma 1, sigma 2, E, so these are the orientation of arbitrary orientation of the one simplices. So we have to preserve the orientation of the two simplices. Each of the two simplices has to be oriented counterclockwise, okay, and the one simplices can be oriented arbitrarily. Okay, So these are the arbitrary orientations of the underlying one simplices of the central rectangle. Okay, so let me write it here. We orient each two simplex sigma I of L in the counterclockwise direction. Counterclockwise direction. And orient the one simplices arbitrarily. Okay, all right. So a possible orientation of the one simplices in the central rectangle on the left is shown on the right here. Okay, that I'm doing now. So I'm zooming in the central rectangle here in the complex L. Right. Okay, so let me call this bottom edge E5, the right edge E6, the top edge E7, and the left edge by E8. And along the diagonals, the edges are denoted by E4, E1, E2, E3. Okay? And the corresponding two simplices, there are 4 two simplices, bounded by this central rectangle. These are sigma 4. Each of them is oriented counterclockwise. This is sigma 4. This is sigma 1. This guy is sigma 2. And this is sigma 3. Alright, this is one possible orientation of the one simplices belonging to the the central rectangle of the complex, the underlying complex L. Okay, now the following statements hold. The following statements hold. So the first being, every one cycle of the complex L is homologous. We know what it means by homologous from the first part of the algebraic topology course. Homologous to a one cycle carried by BDL. Okay, so if I just take one cycle of this on this complex L, that is going to be carried by the boundary of this complex L. Okay, so that one cycle will have value 0 on on each of the one simplices that does not belong to the boundary of this complex L. Okay. All right. So this is the first statement, and the second statement is if D is a two chain of L and del 2D, okay, which is a one chain, right? So after acting the boundary operator del 2 on this two chain, we'll have a one chain. We know that del 2 and del 2 is carried by boundary of L if these two things hold. If D is a two chain of L and del 2 of D is carried by boundary of L, then D is a multiple of the two chain sum over all sigma i's. Sum of all sigma i's as I runs, in an index family. Okay. Of course, it runs over an index, a countable set, because there are countably many two simplices here in the complex L. Okay. All right. So this is the statement of lemma 1. Now we are going to prove it. So I'm going to keep the two figures here, and then erase the bottom part of the statements, right? Okay. So here is the proof. So we are going to prove the second statement first, okay? And so let us zoom in the left rectangle in the complex L, this one, okay? And and we can do the orientation arbitrarily this way, okay? So let me draw the picture of this rectangle here. Excuse me. This is the zoomed in rectangle of L, of the complex L. All right. So this is E, and let us label the one simplices by B, A, F, and C. So each of the two simplices is oriented counterclockwise. This is sigma 1, right? And this is sigma 2. Okay. All right. So let sigma I and sigma j in this sum have an edge E in common. Okay. So see the left figure. So have a look at the left figure, and you'll see that these two simplices have the edge E in common. So we know that the given two for the given two chain, we are given a two chain according to the statement of the lemma. For the given two chain D, delta 2 D is carried by boundary of L, right? This is given. So since delta 2D is carried by the boundary of L, its value, the value of delta 2D on the edge E must be 0. Delta 2D on edge E is 0, right? So we have oriented, so we are supposed to orient the one simplices arbitrarily, okay? So a possible orientation is suggested here. So let us now focus on the contribution of sigma 1 and sigma 2. Let us focus on the contribution of sigma 1 and sigma 2. Excuse me, can you please close the door? Satya? Let us consider the contribution of these two simplices in this sum. So so the value of this two chain D on sigma 1 is n1, while the value of this two chain D on the simplex on the two simplex sigma 2 is n2, right? So the value of D on sigma 1 is n1, while the value of this two chain D on sigma on the two simplex sigma 2 is n2. Okay, right. Now let us write down this delta 2 sigma 2 explicitly. What is delta 2 sigma 2? In this case, delta 2 sigma 2 is minus a minus a minus b plus and minus e, right? This is delta 2 sigma 2. Okay, this is the one chain, and we can also compute delta 2 sigma 1, which is going to be equal to e minus c minus f. Okay, good. So that the value of the one chain, the value of the one chain delta 2D on E becomes what does it become? Um, um, so the value of d on sigma 1 is n1, so it becomes n1 minus n2, right? Right. Okay, but we know that delta 2d is carried by the boundary of L. In other words, delta 2, the value of delta 2d on the edge E has to be 0. So we want n1 minus n2 to be equal to 0, which implies that n1 is equal to n2. That is, the value of the 2 chain D on sigma 1 has to be the same as the value of the 2 chain D on the 2 simplex sigma 2, right? Okay, so this way one can prove that the value of the 2 chain D on all the 2 simplexes sigma i's involved here are the same. Okay, so proceeding the same way one can prove that. Okay, straightforward. In other words, all the ni's in this expression ni sigma I, in the expression of this 2 chain D, okay, all these ni's have to be the same. All right, in other words, D is an integral multiple of this 2 chains sigma, sum of sigma i's. Okay, good. So this way we prove the second part of the two statements. Now let us prove the first part. Okay. Okay, so we need the figure again, and it's a kind of rough figure, it cannot be accurate. So all the 2 simplices are oriented counterclockwise. Okay. These are the arbitrary orientations of the 1 simplices corresponding to the central rectangle. Okay, so let me zoom in the central rectangle here, and which looks like this. This is E5 labeled by E5, E6, E7 and E8, and this edge along the one of the diagonals is labeled by E1, this one by E2, this one by E3, this one by E4, and the two simplices, this one by sigma 4, this one by sigma 1, this one by sigma 2, this one by sigma 3. Okay, good. Now a given one chain C of L, so if we take a one chain C of L, right, and it must be given by the following expression, right? C is equal to sum of all the expressions Ni Ei, where I is not in the set S. I'll explain what the set S is in a while, plus the sum over all the i's belonging to S, sum of all such expressions Ni times Ei, okay, where I runs in the set S, where S is this finite set 1 2 all the way up to 8. Okay, there so there are eight integers, 8 positive integers here. Okay, so the 8, so E1, E2, E3, E4, E5, E6 and E8 are the one simplices corresponding to the central rectangle. Okay, there are 8 one simplices involved in the central rectangle. They are denoted by E1, E2, E3, E4, E5, E6, E7 and E8. So that, and these contribution corresponds to the ones to the one simplices which are not involved in the central rectangle. Okay, so that the value of this one chain C on the one simplex E1 is N1, right? Now define the one chain C1 prime by the following expression. C1 prime is equal to C plus del 2 N1 times sigma 1. This is our equation number 2. This is our equation number 1. Okay, we know the value, what N1 is. N1 is the value of the one chain C that one starts with on the one simplex E1. Okay, this one simplex E1. So we are given this one chain C. We know what the value of this one chain C on E1 is, and that is N1. With the use of that N1, we defined this new one chain C1 prime that is homologous to the given chain C, the given one chain C. Okay, so now from 2 one immediately sees that C1 prime is equal to, now just replace 1 in equation number 2 so that we get this, right? Sum over all i's Ni Ei plus sum over all i's again. Okay, sum over all i's that don't belong to S, and here the sum over all i's that belong to S. Ni ei plus n1. Okay, now I have to read del 2 sigma 1, right? What is del 2 sigma 1? Del 2 sigma 1 from this read out the boundary of this 2 simplex, and you'll get what? N1 times E5 plus E2 minus E1. Okay, all right, but you see that in this expression there is one N1 E1, right? And you get minus N1 E1 here, so that the contribution of E1 drops out in this expression. So grouping everything together, you get the following expression: sum over Ni prime Ei. I is not equal to S prime. Here S prime is a new set, plus sum of all the expressions like Ni prime Ei, where I is in the set S prime, where S prime is a new set, so that we get from S by excluding 1. So it starts from 2, so there are 7 integers here: 2, 3, 4, 5, 6, 7, and 8. Okay, and Ni primes we can always find, can find for some Ni prime belonging to the group of integers. This is our equation number 3. Okay, good. So therefore we see that C1 prime, the way C1 prime is defined by equation number 2, is homologous to C, where C1 prime is a one chain that vanishes on this edge E1. Okay, in other words, by redefining the one chain, okay, you push it off the edge E1. Okay, so we have seen this technique earlier in the first part of the course of algebraic topology. Okay, so this is not something new, we have done it before. Okay, so now we are going to push it off the edge E2. How do we do this? So let me erase this writing here, the bottom part. Now so I just erased the expression of C1 prime, right? So that equation number 2, we need that equation. What was that? Equation number 2 was C1 prime is equal to C1, is C plus del 2 N1 sigma 1. Okay, this was equation number 2, and from this equation we see that the value of C1 prime we don't need this. I think I mistook the equation number in the notes. I need this equation. C1 prime is equal to Ni prime Ei, where I is not equal to, not in S prime, plus n sum of Ni prime Ei, where I is in S prime. Okay, I need this one, equation number 3, and from this we see that the value of the value of C1 prime on E2 is S prime is this set, right? 2, 3, 4 all the way up to 8. So the value of C1 prime on E2 is N2 prime. Okay, which is an integer. With the help of this integer value N2 prime, we define another one chain C1 double prime, which is going to be homologous to C1 prime. This one chain C1 prime plus del 2 N2 prime sigma 2. Okay, this is I call this equation 4a. Okay, so now plug in the value of C1 prime from equation number 3, and this now reads Ni prime Ei, where I does not belong to S prime, plus sum of Ni prime Ei, where I belongs to S prime. Okay, plus N2 prime. Now look at this figure, and when I apply the boundary operator del 2 on this 2 simplex, well, not 2 simplex, it's actually elementary 2 chain, right? Sigma 2. Then I get N2 prime E6 plus E3 minus E2. Okay. All right. So see that S prime is this set, right? So there is N2 prime E2 in this sum, and that gets cancelled against this contribution N2 prime minus N2 prime E2 here, so that in this expression there is no term containing E2, and you can rewrite it always as sum of Ni double prime Ei, where I does not belong to S double prime, plus Ni double prime Ei plus sum of Ni double prime Ei, where I belongs to S double prime. Here S double prime is this set starting from 3. Okay, this way you get rid of the contribution of E2 by redefining your one chain, and in other words, the one chain C1 prime is homologous to the one chain C1 double prime that has values 0 on the edge E2. Okay, so this way you further push the one chain off the edge E2. All right, good. So this new expression is equation number 4. Okay, so now let me erase this part. So from that equation number 4, the one that I just erased, one finds that the value of the one chain C1 prime, the value of C1 double prime on E3 is N3 double prime. Okay, so now I define a new one chain called C1, and that is defined as C1 double prime, the one that we just found, plus del 2 n3 double prime, which is the value of C1 double prime on E3 times sigma 3. This is our equation number 5a, and from which you see that I just plug in the expression of C1 double prime that we found earlier. Sum of ni double prime ei as I for all I does not belonging to S double prime plus sum of ni double prime ei where I belongs to S double prime plus n3 double prime. Now we apply the boundary operator on this elementary 2 chain sigma 3 here to obtain minus E3 plus E7 plus E4. Okay, so there is an N3 double prime E3 here in this sum. Okay, that cancels against this minus N3 double prime E3, so that there is no contribution of E3 in this sum, the total sum, so that we can write it as Ni triple prime Ei, where I does not belong to S triple prime, plus sum over all I belonging to S triple prime, Ni triple prime Ei with a new set S triple prime, which is the set of 4, 5, 6, 7, 8, 5 integers. This is our equation number 5. Okay, good. Now let me erase everything. So we have just seen that C1 double prime is homologous to C1 that vanishes on the one simplex E3. Okay, so combining equation number 2, 4a and 5a, we can write C1 as C plus del 2 n1 sigma 1 plus n2 prime sigma 2 plus n3 double prime sigma 3, where these three values are integral values. n1, n2 prime and n3 double prime are all integers. This is our equation number 6. And we have seen that if C1 is defined this way, then C1, the value of C1 is going to be 0 on all these three simplices, E1, E2 and E3. Okay, good. Okay, now so let me draw this figure. We have been able to push our given one chain of the 3 1 simplices, and let me draw a subcomplex that one obtains from the given complex L. Okay. Okay, so this is a subcomplex that we denote by N. All right. So it differs from the complex L in the sense that it does not contain these three edges that were present in the previous complex L. Okay. So we have seen that. So we started with a one chain. Sorry. Oh, we started with a one chain. Of course. Yeah. Sorry. So we started with a one chain C on the given complex L, and we have been able to prove that one chain C is homologous to a one chain C1 that is carried by this subcomplex M of the given complex L, right? So let me put a caption of this figure. Subcomplex of L carrying the one chain C1 that is homologous to the given one chain on L. Okay. Now, following exactly the same procedure, okay, the procedure that we carried out to push the given one chain C of these three one simplices one at a time, right? So if we follow the same procedure, then we can push the one chain of some other one simplices as well to arrive at the following figure. Okay, so let me draw another subcomplex here. I'm not going into the detail of the calculations, they are left as exercises. Okay, let me call these vertices as V prime, V double prime, V triple prime. Okay, so now I leave it as an exercise for you to check that you can similarly push the one chain of, say, this one simplex, this one simplex, this one simplex, this one simplex, this one in simplex, this one simplex, and so on like this to arrive at this sum complex. Okay, so you can prove that the one chain that you get here, okay, so you have proven that we have proven that the given chain, the one chain C on the complex L is homologous to a one chain carried by the subcomplex M, right? Now you got to prove that the chain, the one chain C1 that you have here is homologous to a one chain carried by this subcomplex. Okay. So in other words, you end up proving that the given one chain C on the complex L is homologous to a one chain carried by this subcomplex, right? So let me put the caption here of this figure. Subcomplex of L carrying the one chain C2 that is homologous to the given one chain C on L. Okay, so you actually prove that this one chain, the one chain carried by this subcomplex is homologous to the one chain carried by this subcomplex, right? But previously we have proven that the given one chain defined on the complex L is actually homologous to the one chain carried by the subcomplex M. So that way you prove that the one chain carried by by you prove that the one chain that one defines on the given complex L is actually homologous to one chain carried by this subcomplex of L. Okay. Good. So we have gotten this far. We don't need this subcomplex anymore. So let me get rid of this bottom figure. Okay. So let us call this one chain C2. Okay, so C2 is carried by the subcomplex drawn in figure 4, in figure 4, and is homologous to the given one chain C on the complex L, right? I want you to prove it explicitly, okay? So I leave it as an exercise. Now, if the given one chain C on L is also a cycle, okay, then the chain carried by this subcomplex M, the chain C2 carried by the subcomplex of L is also a cycle, right? Then since they are homologous, then the one chain C2 homologous to C and carried by the subcomplex drawn in figure V4 is also one cycle, right? Since they are homologous. Okay, so what does that mean? It means that delta 1 C2 is 0. Right? So let me, in figure 4, let me label these vertices as well. The vertices here on the central rectangle, V5, V2, V1, V4, and V3. Okay, so since C2 is a one cycle, del 1 C2 must vanish on each of these 5 vertices, V1, V2, V3, V4, and V5. Okay, all right. Now suppose C2 is a one cycle whose value on the one simplices V comma V5 is a one simplex, right? V comma V5 is an oriented one simplex directed from V towards V5. V5 to V1, V prime to V4, V double prime to V3, and V triple prime to V2, right? So this one, if you want to put the orientation here, from V5 to V1, from V prime to V4, from V double prime to V3, and finally from V triple prime to V2. Okay, so there are 5 oriented edges, right? So let us assume that the value of this one cycle on these oriented 5 edges are n1, n2, n3, n4, and n5 respectively. Okay. Well, I need room. That's good enough. Okay, so since C2 is a one cycle, right? We know that del 1 C2, we have already written down here, del 1 C2 is equal to 0. But the value of del 1 C2 on say V5 okay. So when you compute, so when you apply the boundary operator on these elementary bond chains, what do you get? So when del 1 acts here, you get a v5 minus v1, okay, and that going to be multiplied with n1 here, right? Because the value of c2 on this one simplex is n1, right? So you get this one, and when you apply del 1 here, you get n2 times v1 minus v5, so that the value of del 1 c2 on the vertex v5 is n1 minus n2, right? Is n1 minus n2. The value of del 1 c2 on the vertex v1, see that here is n2. The value of del 1 c2 on the vertex v1, okay, I think I gotta count this one also. So this is n2 minus n1, right? Del 1 c2, right? v5 minus v1, v1 minus v5. Sorry, this is v comma v5, so this is not v1, this is v, okay? So for where is v1? Okay, so on n2 is just v1. The value of del 1 c2 on v1 is just n2. The value of del 1 c2 on v2 is so from this we get n5 times v2 minus v triple prime. So it's n5 on v2 is n5, on v3 is n4, on v3 is n4, and on v4 is n3, this one. On v4 is n3. Good. So since we want del 1 c2 to vanish on all these 5 vertices, we must have n1 minus n2 to be equal to 0, meaning that n1 is equal to n2. We want n2 to be 0, n5 to be 0, n4 to be 0, and n3 to be 0. And since n1 is equal to n2, n1 is also 0. Okay, so we arrive at this equation. n1 is equal to n2 is equal to n3 is equal to n4 is equal to n5 is equal to 0. So what does it mean? It means that the one cycle C2 is carried by the boundary of the complex L, okay? Because no, since so we started with the one cycle C2 and we took the values of this one cycle on these one simplices to be expressed by this integer values n1, n2, n3, n4 and n5, and we arrived at the fact that all these integers are identically zero, meaning that the value of this the values of this one cycle C2 must vanish on all the oriented one simplices not belonging to the boundary of L. Okay, so which means that the one cycle C2 must be carried by the boundary of L. Okay, good. So this was the proof of lemma 1. We take a break here now. In the second segment, we'll state and prove our first theorem for the first lecture, which concerns the homology groups of the two torus. Thank you for attending the first segment of the first lecture for the course of Algebraic Topology 2.